Okay, welcome everyone. Today's lecture is, I would say, advanced material. We're going to talk about latent dynamics models. So dynamics models in latent space that are also stochastic, not deterministic. So we want to keep around different possibilities for future. Now, the topic covered today are not part of quiz 2. We were planning to cover it Wednesday, but we didn't have time. So the papers that we're going to cover today will not be part of quiz 2, okay? They're going to be part of quiz 3. However, we're very close to completing our model-based reinforcement learning, let's say, theme, okay? And at the end, once we cover everything, for today, I have planned stochastic latent dynamics and graph-based models. And once we cover everything, then on Wednesday, we'll make a very nice, puzzle where we piece different models together, the pros and cons, where are the open research problems, and so on. And then we're just going to move on to intelligent exploration, offline reinforcement learning, sim to real, domain adaptation, meta learning, and whatever other topics, whatever we have time to cover till December 9th, which is our last day of classes. Okay. All right. Do you have any questions? Okay. All right. So this is to be honest, it doesn't look very clear. I don't know. To me, it looks a little bit too bright today, or that's how it usually is. I'm not sure.
It might have more lights on.
I will have more light. So we may need to switch them off or something. Okay. So these are the two categories that we have, let's say, put down for dynamics models. We said that earlier dynamic models would predict the future in a pixel space, and then to create rollouts, which means imaginations of trajectories, they would take the output image and feed it back at input. I'm going to keep going. Okay, so these are what the first works did. Why? Because it was conceptually simple. We have targets for the future is the actual image. So then we try to predict that image. The downside was you learn to predict things that are irrelevant to your task. Okay? So then we threw away these models and we said instead we're going to train models end to end, but in latent space. Okay? So we'll take representation networks, we'll take observations, and jump to some compressed latent space, which so far that latent space has been one-dimensional vectors, to be honest, that summarizes the image, okay? And then would learn dynamics over those latent 1D vectors. And we said that for this not to collapse, not to map every image to the zero vector, you need to be predicting, let's say, quantities that you need to read off your model. An obvious quantity is the words. Because when you imagine trajectories, you want to know whether you land on states that have high reward or low reward. The problem with rewards is that they're sparse, and thus they're a very weak learning signal. So the other big idea we explored was to predict other task-relevant quantities, okay, like actions and values. And these are all predicted from the same latent space, and gradients backpropagate all the way to the representation variables, to the representation parameters, right? So we learn to compress sets of images into latent vectors from where rewards will be predicted, values, and actions. So this is what we saw for mu0, but also we saw the same thing for TDMPC. In TDMPC, we saw the additional loss about consistency of that latent state, if you remember, that was missing from mu0, which helped, decrease the amount of training data. So today, so this is what we focused last time. All right. So today, the new thing is essentially this. We will be sampling the next state. We'll be sampling the next state. We don't have a deterministic mapping of the next latent vector condition on the current state, latent, and action. Okay. That's the only difference. Is this clear? Okay. So here it is. We have a bunch of observations. We have a representation network that takes us all to the latent space. We have our dynamics network that essentially predicts the next state. And then we have things that state vector is supposed to be predicting correctly, One of them are rewards, other are values, actions, and some, the models that we're going to see today will also be reconstructing observations. Okay. Now we all agreed that this is a bad idea. Okay, because maybe it's better than predicting images, but still you need to be predicting quantities that suffice to reconstruct the image. And indeed, you will see that we're going to have losses that fight one another. One loss would say, oh, make a latent space from where I can reconstruct the pixels. And the other will say, oh, make a latent space that I can accurately predict. All right. So then, one loss will tell you, don't include the clouds. I don't know how to predict them. And the other loss will tell you, oh, but I need the clouds. I want to be predicting those pixels and so on. So there is this trade-off over there. Now, a good question would be, can we just get rid of those reconstruction losses? Potentially, yes. This precisely what efficient zero does. There is no reconstruction, but there is a latent, latent states, as we say, consistency loss. Okay, so we never go back and reconstruct pixels. We just encode the current state and predict the future, and encode the future and encode the future image, and we make sure our predicted vector is similar or close at least to the latent vector for the next observation. Okay. And that I just want to make sure this extra consistency loss doesn't put any stress on the latent space to predict any pixels. Okay. We can still remove any cloud irrelevant task information from the latent space and still be consistent. Okay. All right. Let's see how we're going to do these things. So let's start simple and let's try to adapt our PETS framework to operate not from low dimensional state as you have in your homework, but rather from image observations. Okay, how would this happen? Extremely the same way that we've seen. We'll take the images and we'll encode them, okay? And this will give some state vector, and then we'll have a model. We'll take a state vector and the action, we'll predict the next state vector. And those latent vectors are going to be trained to reconstruct those observations as well to predict the rewards. Okay, and it is absolutely necessary to predict the reward. Reward prediction is part of the dynamics model. Why? Because of the way you want to use your model, right? You want to be imagining tons of trajectories. We're going to see at the end a paper that trained from 400 billion imagined trajectories, and every trajectory need to have additional reward information, how good or bad it is, okay? So here's how it's going to look like the planning. We'll have, after we learn this model, what we're going to do is we're going to start from an actual observation here, this Omicron 1, which will code, this is our representation network. We'll jump to our latent space. We're going to condition on a sequence of actions, exactly, right? That was cross-entropy method, right? It was searching, and that during search, it would hypothesize action sequences, fit them into a dynamics model, and evaluate them. Okay, that's all. Now, the only difference here, guys, is that as you see, those state variables are circles, which means they're stochastic. They are not squares, but we don't know yet how to do that. So we just put it there down. So here is, so given the initial observation and a bunch of action sequences, here are these dots, we're going to evaluate those different actions, different trajectories, and pick the one that maximizes the rewards. That's all. So we're going to be planning in the latent space. And we've seen this already. TDMPC was doing something like this. Then we'll execute the first action and repeat. All right, exactly this also we saw in the last lecture. This is called model predictive control. You don't apply in the environment all your inferred actions. You apply the first and then replan. Okay. So instead of just decoding rewards, let's add the ideas from mu0 of predicting also, actions and values. Okay, this is my latent state, and I'll train it to also predict an estimated of the value of that state as well as my policy. And my policy can have either continuous actions or discrete actions. Both are okay here. And I'm saying this because in mu0, we only saw it for discrete actions, right? So they had to, have a different paper to cover continuous actions, which is highly non-obvious how to do Monte Carlo research with continuous action. Okay. So then how is it going to look like? Well, again, I have my observation and I jump into latent space and my policy is attached to my state. So I sample from my policy and then I land on trajectories of which I can compute the rewards and the values and so on. Okay. And essentially learning a policy with this type of model will look very similar to whatever we've seen before. Will be an iteration between three things. Okay. So by the way, here I just put some diagrams about the latent dynamics model, where the only thing that you understand that it is stochastic is from the circle. That's it. I mean, there is nothing else that is different to what we've seen before. It's just the way we're going to train it that differs. The planning, the prediction, the values, these quantities are the same exactly as what we saw in TDC, mu0, and so on. And even this method will be very similar. Again, we're going to iterate between these three steps. We're going to be deploying the policy environment. So we'll collect some environment, let's say, trajectories. We'll use the environment trajectories to learn a dynamics model. And then we're going to learn the policy only in the imagination space. Okay? So the actual environment interactions are only going to be used to train the model. Okay? And policy and value functions will be trained only in imagination space. And now you may say, oh, this is new. Before we were using also the actual experience. The truth is that always that actual experience was so tiny to the extent it doesn't matter. But it's so tiny in comparison to the imagined experience that happens just by, unrolling your model. So nothing so far changed. Just so far we haven't said anything major. Are everybody happy here or? Okay, so just to be clear, simply because, for pets, we didn't have a policy, if you remember, we're using the model just to optimize over actions directly. Here, there will be a policy, okay? So we'll be training this dynamics model, the transition model. This transition model will also have the policy that takes the state, spits out actions, and the value function, okay, that takes that state and spits out the value of the state. Okay, so all of those three will be learned at stage 2. Is that clear? And then you deploy your policy and you collect experience. You go back and you update your model, update your policy and value through the new updated model. You collect imagined experience and so on. Then use your updated policy to collect more better real experience and so on and so forth. And we've explained early on when we started talking about model-based RL about the importance of iterating between dynamic model learning and policy learning. Does anybody want to repeat why we need to iterate? Mm-hmm.
Because we want an understanding of the space of the environment where the policy will go to.
Yes, because if the policy goes in places where your dynamics model doesn't have training data from, your model will be inaccurate and then your policy cannot be optimized there. That's why we need to be iterate, exactly because of this distribution mismatch that can occur. Okay, when you deploy a policy, you may land on states that your model was not trained on. Okay, so now we're going to see the code, which will look a little bit, how to say, scary, but then we're going to make a big parenthesis. We'll talk about variational autoencoders, and then we'll get out of the parenthesis, and then we'll see how those conditional variational autoencoders are applied in the dreamer case. Okay, and just to give you the big picture of today's lecture, which is a plain lecture, because, it depends how much, actually, I'm not sure how fast or slow it's going to go, but the first chunk of this lecture is about Dreamer, version 1 and version 2. Dreamer is just an algorithm for reinforcement learning that learns in a latent space. It uses dynamics models that are stochastic. Dreamer version 1 uses latent variables in dynamics models that are Gaussian. And Dreamer version 2 uses latents in the dynamics models that are discrete. This is the big difference. Now, there are tiny little bit difference on version V2. For example, as I will see, the policy will be trained both through backpropagating through that differentiable model, but also through policy gradients, while in Dreamer 1, we only have learning of the policy through backpropagation through the dynamics model. That's one change. But I think, just to have it clear in your mind, in both cases, we have latent dynamics. We learn policy and value functions in the latent space. We're going to be sampling insane amount of latent imaginations, like rollouts. In the first case, this dynamics will be stochastic using Gaussian latents, and in the other, discrete latents. Okay, and we're going to be sampling in the first case from Gaussian distribution, in the second case from categorical distributions. This is the first chunk of the lecture. Is that clear? Okay, so let's see. All right, by the way, the best practice for today's lecture is to go to Dreamer V2 repo, look at it and so on, play with it, etc. I mean, we'll try to go into details. It's going to be a bit scary at some point how detailed we're going to be, but unless you implement it, you won't be able to understand it. And the truth is that in this semester, there's no homework on those. We have a homework on mu0, which is deterministic, okay? Okay, so let's see how the... So first of all, what are the pieces that we need to be learning? So first of all, we have this representation model that takes our previous state and action and observation, and, well, I don't like this one, that jumps from the observation space to the latent space. We have the transition model that given a latent state and an action takes you to the next state. We have the reward, the policy, and the value, which are essentially decodings of the latent space. And the one decodes the reward, the other decodes action, and the other decodes the value. Okay? So we initialize our network randomly. Now, you need to understand that as you're training the value, okay, the gradients propagate all the way to the representation network. So that's one thing not to be confused. So where we show, for example, that training the value is going to be again a least squares problem. Like as usual, we're going to have value targets. We're going to be regressive towards those. Those gradients do not just update the part that takes the state and spits out the value, can update all the way through the representation network and so on. Does this make sense? Because the whole model is end-to-end differentiable. But let's see how things look like. All right. So let's see different. So the easiest part is here, where we have a policy. In the beginning, it's going to be random, which deploy in the environment by adding also exploration noise, because we need to be make sure we maintain sufficient exploration. And we collect those environment interactions into that buffer D environment. Okay, we use that buffer D environment to learn the dynamics. Okay, here is precisely the transition model, and the transition model is stochastic. And that's why we're going to train with variational inference in a way that we'll explain. Is that clear? Okay, so this we keep this in our mind that we need to come back to that. Now, once I have a model, we're going to show you now how do you train your policy and value function. The simplest thing is the critic, which is just the value function. We're just going to find a way to compute value targets as we usually do. For example, immediate reward plus gamma and the estimate over V for the next state. Okay, as simple as that. We're going to be bootstrapping. Specifically, we're going to be using n-step targets. Okay, so not just immediate reward plus gamma V of the next state, but like immediate reward plus gamma, immediate reward, gamma square, immediate reward plus gamma to third, and so on. Specifically, they have these very fancy targets where they do a weighted combination of multi-step targets for different horizons. All right. You can see we have the equation here. Is not very important. You can just think that it is just an n-step target. There is nothing, crazy there. The big difference is that those targets are computed where? From imagination trajectories. Do you see? We're going to be using everything here in imaginations when we compute our targets. Now, once you have your targets, learning of your critic is just what? A least squares problem, as has always been in our course. All right. Is that 100% clear? So we've been training so far value functions using actual trajectories, right? I mean, I'm pretty sure we saw this also from the previous. Let me think. I don't remember if mu0 was using, imagined trajectory for values. But here we're going to be using latent imagination rollouts to form targets using the estimated rewards and the values of the next states, which are going to be the estimated next states from your model, to form targets for your value function. Okay, so this is what happens here for updating the critic. Now, how do we update the actor? So by the way, we still have an actor critic framework. but the way we update the actor is not through this grad log p theta multiplied with advantages. This happens in the second paper. Here, we essentially backpropagate through the value function. We know the values. Okay, these are the value targets for every time step, and I update the parameters of my policy to maximize the values at each one of those states. And why I can do that? Because now I have a differentiable path to go from the parameters of my policy all the way to the value of every state in my trajectory. Before, I didn't know how to do that. I didn't have a model. For example, there was no way I could connect my state 1 to future states because I had to act in the world. Now I don't act in the world. I have those trajectories, okay? And I can backpropagate, let's say, the error or the maximization of the value at each one of those states all the way to the parameters of my policy. Is that clear? And my policy can be totally stochastic. It doesn't be deterministic. Why? Because I will use the reparameterization trick for Gaussian policies, and I will, use straight-through gradients for softmax policies. And these straight-through gradients, we're going to see it also in a little bit in a few slides from now, because we're also going to use it for the dynamics model. So in high level, these are the details, but now we're going to go into more detail on those. Is that clear, roughly what's going on? We interact, we learn a dynamics model. The dynamics model is stochastic. Then we sample from the model insane amount of imagination rollouts. We compute targets for the value function. We update the value function. And we update the parameters of our actor to maximize the value targets at each state of those latent trajectories. So the interesting thing is that this value and actor update all happen in imagination space. So let's see how this is going to... Okay, so let's see how this is possible. Both of those two red lines require backpropagating through sampling, okay? And these samples are going to be Gaussian samples. So now we're going to talk exactly about this, okay? So let's just relax. We haven't discussed about this before. This is the first time we talk about variational autoencoders. It's actually extremely simple. So here is how the story goes. Imagine that we want to learn a generative model that maps, let's say, random vectors to actual items in our domain. For example, states or actions, okay? Our generative model will transform this random noise into samples from our desired output distribution, which can be a distribution of actions of next states. Now, please do not get confused. In our case, of course, we have an extra conditioning information. When we sample actions, we condition on the state. And when we sample next states, we condition on the present state and action, correct? So first, we're going to see the story about unconditional variational autoencoders. And then right the next slide, we'll see, okay, how do things change if I have conditioning? They change very little. Okay, you just have an extra input into this model. Okay, now the first interesting thing to realize is how can we map random noise into these beautiful pictures, right? You take random noise, here is a two-dimensional Gaussian, and interestingly, simply passing through this function, you can form circles. So indeed you can take a random noise and map it to that image, is because you're going to pass this random noise through very complicated and multiple layers of your neural network, okay? So there is a deep function that connects the sampled vectors to the image. And this, by the way, was precisely the case where we're training generators in the case of GAL, generative adversarial imitation learning, correct? Okay, so let's see. So each sample maps to a sample from the data manifold that I care to model, okay? So sampling from this model means that you sample in the beginning, in the very beginning. So basically those is essentially 50 numbers, each one sample from a constant Gaussian distribution of 0, mean, and unit variance. So sampling means I sample in the input, then the network is deterministic, and then the mapping happens at the end, okay? That's what sampling means here. Is that clear? Okay. Now, imagine that I want to train my model, and usually, okay, we have a Gaussian distribution at the very end, so I'll explain this is a very simple thing. And, I can train this model by maximizing data likelihood, right? So I take a huge integral over all possible z's trying to maximize the probability of my images, of my states, of my actions, or so on, whatever I want to model. Okay. Now why this is difficult? Why this is difficult? I want to ask you something. Do you know how to do that thing? So PZ, as I just told you, is just this very simple, constant Gaussian distribution. So you know PZ, you know the prior of those Z's, correct? Do you agree? Very simple. Doesn't have even parameters. Now the P of x is like the probability of every pixel in your image, given the Z, is again super simple. It's a Gaussian. And the mean of the Gaussian is the output of the network. That's the standard assumption, right? That we have a Gaussian distribution and the mean of my Gaussian comes out of my network. So I say that you know everything here. Do you kind of agree? So my question for you guys is the following. Would you be able to, by the way, this is an expectation, and we know how to approximate expectations by sampling. So does any of you know how to sample few Z's from that prior distribution and form here something that we can update through gradient descent to maximize the data likelihood, or no? How would this look like? Okay, so it would look like this. Essentially, I sample some Z's from the constant Gaussian distributions, okay, with that are, let's say, 20 long vectors, okay? And I just do log px given Z, which, by the way, I know what it is. So this is just least squares. Do you agree? All right. So then the question is, why don't we just do that? Why don't we just do that is the question. Now, I think the first thing that I want you to realize is that I can totally train the parameters on my theta by maximizing this, trying to minimize this approximation to the data likelihood. Okay, maximize. Yes, please.
Isn't it the same issue we ran into before, where whenever you start approximating stuff with samples, you really increase the variance?
Yeah, exactly. This is just, you can do that. You can take gradients. I have even done it and put in a paper in a condition setup as a valid baseline in a conditional case, right? Because in the conditional case, things are a bit more obvious, like it's not like nuts, the things that you need to approximate. But the truth is that this is just a bad approximation. You cannot learn to start generating natural images in this way. Do you see? Why? Because most of the terms here, most of those Z's will actually be zero at initialization time. Do you see? Very few Z's will actually be useful. And if you just say, oh, let me sample 30 Z's, pass them to a network, aggregate the output, and so on. So this is not a good approximation, okay? So nothing useful will come out from here, especially in the unconditional case. So here is the trick. The trick is as follows. There are some great Z's out there, right? But we don't know how to pair the Z's with the right text, with the images, okay? So then we say, what if we create a cheating network? The cheating network. We'll parameterize it. It's also going to be a deep neural network. And we'll call it a cheating network because that network will take into account the X, which is precisely what you want to generate. Okay? So now let's see about this cheating network. So we'll not call it cheat, we'll call it the inference network. Okay, that's fine. So this is Q. It has parameters, let's say psi and so on. And we'll give a distribution over Z's that are likely to produce X. So we train it so that given an X will produce good Z's. Okay. Let's see. So let's start from, this is Px, the probability over natural images that I have, that I want to model. And Px is precisely like this. Exactly, we wrote exactly this in the previous slide. Probability of X given Z and probability of Z. And what can I do now? Well, you can go inside this expectation and divide and multiply with QZ given X. Okay? Imagine you just do this. So now what you have? You have a new expectation over Z sample from QZ given X of these three terms. Do you see that? Or we just going to multiply and divide with the q of z given x. Do you see that so far there is no approximation? Anybody who wants to raise his hand? Her hand? Okay. So now here's what we're going to do. We want to compute log of p of x. So now we need to use the log of that expectation. Okay. But then we're going to push the log inside the expectation. Okay. And log is a concave function. So because of that, the expectation of the log will be smaller or equal to the log of the expectation. Are you also cool with this? So you take you take 2 points on the log, okay? Take the midpoint. The log of that midpoint will always lie higher than the expectation of the two logs, than the weighted sum of the logs. That's what, because it's a concave function, all right? So this is a standard Jensen inequality. Is that clear? Okay, we've used this multiple times. Okay, now we have the logarithm next to a multiplication. So we know what to do. We're just going to break it. So we have the log of the p x given z, great. And here's the log of this other term. Sounds good to me. So how do these terms look like? This looks like the probability of x given z. This is called the reconstruction term because we're going to be reconstructing images from those latent codes. All right. Now the other guy is what? Who wants to tell us what this is? With what does it look like? An expectation over things sampled from some distribution p of the log or q log of p divided by q.
Is a KL divergence?
Yeah, well, is the minus of the KL divergence between q and p. Do you agree with this? Yeah, exactly. So here is so now we form the lower bound of the maximum likelihood of the likelihood of the data or the log likelihood, okay, in terms with respect to the reconstruction error and the KL between Q and P. So our goal is to be, if we want to maximize the log likelihood, we need to be maximizing reconstruction, the reconstruction quality, and minimizing the KL between Q and P. Okay, the other way to see it is we want to be minimizing KL between Q and P and minimizing also the reconstruction error. Okay. So, okay. So does this make sense, guys? Our goal is to pair Z's with X's. Okay. We saw this. Yes, please.
Why is KL divergence a measure of complexity?
Yes. So why we call it complexity. Okay. So because depending on how complicated your prior is, then that's how much you allow your approximate posterior, which is this inference network, to vary. Okay. So essentially you regularize it. All right. To be close to that prior. All right, so here is the interesting thing. This is called variational autoencoder, although it has nothing to do with the regular autoencoders. Okay, it has nothing to do. I would say it's a bit confusing to think that it's super related to autoencoding, simply because there is a term that takes you from X, which is big, to Z, which is small. So we call it an encoder. So when you go from something big to small, you call it that you're encoding. And there's another term that takes you from Z back to X, okay, so you can given Z your sampling axis, which is called the decoding. Does this make sense to you guys? All right, that's it. That's all we did. We started with the likelihood of our data or the whatever we want to sample, to model. we wrote this with respect to those latent variables, divided and multiplied with Q, then put the Jensen inequality to push the logarithm inside the expectation, and then this came out. Does this make sense? So things may not look great yet, but now we're going to go to the next slide to see how we can actually forget about this and try to optimize that. And when we optimize this, we're also going to be maximizing the log likelihood of the data, which is the initial thing we're trying to do. Okay? Yeah, so this is called the variational lower bound. So here is exactly what we're going to be doing. It's all going to be nice and end-to-end differentiable. So let's see what subnetworks we have and from what parameters they depend on. Okay? So, okay, what I see here is we have an image, and then this is encoded. Clearly, that encoder is a new network and has some parameters. And here we're going to be sampling some Z's. Okay. This is the cheating network. This is a cheating network. And here's the decoding that takes the Z and goes back to the image. And when you spit out the image, here you're applying reconstruction. By the way, just to be clear, your goal is to just sample images. Okay, from this to sample images. At test time, how things are going to look like. Now we're talking about training time. But at test time, how things are going to look like. At test time, you throw away the cheating network. You throw away the inference network. This guy is just simply here to facilitate learning of this decoder. Now, as you learn the decoder, then you throw it away and you go back to our first picture and you sample from your Z's, pass them through your network, and get awesome samples from the data manifold you're trying to model. Okay? Is that clear? All right. So that's the first thing we need to understand. Okay. So now I have an image, and then I encode. And then here, what we're saying is, well, we go to that Z. Okay. And this is a distribution over Z's. And I'll consider Gaussian distribution, multivariate Gaussian distribution. And I have the reconstruction error here. This is which is and this KL is exactly that. This is the prior over Z, which is indeed this constant multivariate Gaussian distribution. And this is the output over Z, that is the output of your encoder. So basically, I have some nice colors here. So that's it. So these are the two losses. Okay, so losses and errors are going to be computed here at these parts of the network and will propagate all the way to the parameters of the encoder and the decoder. Is this clear? Okay, well, to me, it doesn't look super clear. For example, how we're going to be sampling here these. How we're going to backpropagate through sampling. I mean, do you guys know how to backpropagate through sampling? So just to be clear here, so this yellow term, so let me tell you one more time. We have two losses, the yellow and the orange. The yellow will touch the encoder weights, and the orange will touch both the decoder and the encoder weights. Okay, and just what we said is that at the top of the encoder, we're going to be computing, the mean of a Gaussian distribution, the mean and even the covariance, full covariance matrix of that distribution over Z's, from where we're going to be sampling those Z's, right? And in fact, we said that the KL of that distribution that will be parameterized by our cheating network better be close to the prior, which is this zero mean unit diagonal identity covariance Gaussian distribution. Okay, but my problem here is that although this is just a standard least squares, okay, so I'll have an image, fit them in, and make sure that we reconstruct the same image, and that's why it's also not autoencoder, because you feed an image and you reconstruct the same image, but the bottleneck is latent. You see, you're sampling in the middle. So how we're going to backpropagate through that sampling of the Z's? That's the big question here. Yes.
Isn't that something that you do with GANs? I know there's a trick that you can do to sample through to backpropagate through sampling. I think we looked at it with Guile. Am I making that up?
Great. So your calling is saying in GANs, how did we propagate there through sampling? That's what he's saying, right? This think. Okay, let's keep this thought in mind. Yes.
Yeah, it's the reparameterization trick where you just sample from a unit normal distribution and multiply by the mean and variance, or scale it up to the mean and variance, so it has
Scale it with the variance and not the mean. Okay, so this is another thought. Okay, and whoever wants to reply to your colleague with the first thought, he said we did the same thing in GANs. Please, you should think and try to raise your hand. But now your other colleague said something else. He said, wait a second, when we sample from a general Gaussian distribution, for example, this is a general Gaussian distribution parameterized by mu x and sigma x, okay? All right, which essentially some numbers that come out of your network. You feed to the network X, it spits out numbers for your mean and your covariance. He says you can do exactly the same thing by sampling from a zero mean and identity covariance, right? And then scale with the sigma, or at least you need to do the Cholesky decomposition. Let's forget about the full covariance and put some, identity covariance matrix, okay? So for each one of them, you multiply with the sigma I of the I coordinate and not the mu of the corresponding coordinate. And here are your samples from the target mu x, sigma x. Do you remember when we did that? Actually, I can remind you, we did that when we talked about the natural evolutionary strategies. Do you remember, guys, there, what we did? So now your colleague is saying, no problem, I'll be sampling from that constant. Each time I want to, compute an example and in my batch, I'll sample from that constant, add the mu and x, and now everything is end-to-end backpropable, right? There's no sampling now anymore. Or there's sampling outside, who cares? Okay? Does this make sense? So for every example, I also sample from constant distribution. I feed it through the network here. Actually, I have the picture. Here, this is what your colleague is saying. He's saying, feed the image, get the mu and x, go to the epsilon, okay? Not to be confused with the prior. Completely different stuff here, guys, okay? This is just for the reparameterization. So you go, you sample your epsilon from there, you find Z as epsilon sigma, you feed it in your decoder, do the reconstruction, and now, hop, you can backpropagate all the way, no problem, right? There's no sampling now. All right, this epsilon for that specific, like PyTorch, we'll see that constant. Epsilon is a constant for PyTorch. No. Yes.
I have a question. For each step of these, would you generate
multiple or one?
Yeah.
Whatever you like, you can do. You can do one, you can do multiple. Yeah. Many people would do one. Okay.
Does that not increase the variance?
Yes, it does. It does. But you pass it multiple times and so on. So whatever you prefer. Yeah. Good question. Great question. But do you agree with your colleagues' reasoning? Okay, great. So variational encoders are all nice and simple because they model the latents as Gaussians and they exploit the reparameterization trick to train end-to-end the inference network and the decoder. All right? End-to-end. You give them a bunch of images. They say, don't worry, here is a generative model. And then at the end of test time, you throw away the cheat network and you just use the decoder. You sample from the Z and you decode and you get the images. And the truth is, guys, that you're going to cover those in details in your deep learning course. So we don't need to go through detail. They're going to tell you about pros and cons of GANs versus VAEs. VAEs are blurry, but you can compute the likelihood, while GANs, you cannot compute the likelihood. And you're going to talk to you about fusion models and all other generative models you want to know about. But for our purposes, this is enough. Okay. Now let's go back to your colleague's comment that says, in GANs, didn't we do something like that? Does anybody want to tell us how we train Kyle, given that also quiz 2 is coming up, right? So yeah, who would like to tell us? Did we use the reparameterization trick there? Also, we had a generator. That's what your colleague is pointing out. That would take latent vectors and spits out images. Okay, so let me tell you then. So the amazing thing is that GANs are not trained with a reparameterization trick. You just sample from that initial vector and feed it, and then you pass this to a discriminator. And they do mode collapse. They suffer from mode collapse, meaning they model only one part of the distribution of data and not another, but that part of distribution that they model it very accurate without blurring and so on. Okay? So to train GANs, we indeed were sampling the beginning of the network and just feeding it in. And then we're jointly training the generator with signal from the discriminator, if you remember. And there was nowhere that thing. There was no reconstruction loss. Isn't this, do you see? This is super important. There is no reconstruction. You feed the latent vectors, and in aggregate, you judge, did what I generate look like distribution? You just do a distribution matching loss, not where this Z was going to, what image that Z should generate. So there's no pairing problem between Z and images because there's no supervision on the image that you generate. Do you see? So completely different. But this is an excellent point that you, now that you brought it up, to discuss the differences. Okay. Other questions here? This still looks super far away from Dreamer. Okay, so let's just try to bring it a bit closer to Dreamer. All right. So first of all, we need to go from variational encoders to conditional variational encoders. That's the first thing. This is super simple, though. This is simple. So what does this mean? It means that instead of just having the Z as input and try to model the manifold of images or of actions, what all possible actions I can do, and so on, I'll feed an extra conditioning information X, and now they're trying to generate Y. So don't confuse yourself. In the previous slide, we're generating X's. Now we're generating Y's. And X's is conditioned. It's as input to our network. Is this clear? Okay. So, and for example, if you want to predict dynamics, clearly the conditioning information will be state and action. And the output will be next state. If you want to learn policies, what would be the conditioning? A generative model over action, let's say. Yes?
Condition would be the state.
Yeah, only the state. Correct? Yeah. Okay. So again, the same story will happen, that now I need to maximize the conditional data likelihood, probability of Y given X's. And of course, I can, at the output, I can totally add this Gaussian. That essentially my network spits out the mean, here f, x, comma, z, and so on. And the z comes from this constant, as we said, zero mean and identity covariance. And I can totally try to directly maximize the data likelihood, and I will have the same problems as before, although in a lesser extent, because now these conditional distributions are much, of course, they are much pickier than, of course, trying to generate all images. If you tell me what's going to happen given this image, and you moving to the left, there are much fewer things can happen than if I tell you generate an image. Do you see what I mean? So that's why even this very obvious, baseline of just, sample some Z's and feed them there and, do least squares, it's going to give you something. Okay. All right. But we're not going to do that. We're still going to use the same thing as before. We're going to train this cheating network, which we call it cheating or an inference network because it has access to what we're trying to generate, which is the Y. But this time, not only is going to look at the Y, but what is allowed to look, the X, the conditioning information. So as you see here, the Q takes as input both the X and Y. And then here is the expectation. Yes, we'll divide and multiply with the Q, Z given X and Y. It will take Jensen and code to push the logarithm inside the expectation. We'll break this into terms, and we have exactly the same thing as before, a reconstruction and a KL between them prior and the approximate posterior. Do you see that everything is exactly the same? Okay. So now if you go to our nice picture, how is this picture different? Who would like to tell us the difference of this present picture to the picture before? Who would like to describe this picture? Okay. Do you want to describe or yes?
Now has X coming in.
Okay, X coming in for sure. This is also at test time, right? So at test time you fit here in the decoder. This is what happens at test time, but at the training time also that X enters into both in the encoder and the decoder. Okay. I mean the rest I must say look pretty similar to before. The only thing that is missing is the visualization of the reparametrization tree, simply because it's exactly the same as the previous slides. Okay, now let's try to see how can we adapt the conditional case for the case of latent, stochastic latent dynamics models. Any questions so far, guys? Yes. A little bit louder, please.
Oh, could you explain why X enters the encoder?
Yeah, why X enters the encoder, right? Okay. Maybe what you're trying to say is that since the encoder has access to Y, which is precisely what you want to generate, Y needs to also have additional information about X. Is this what you mean? Okay. All right. So here is the thing. Because it might be that one state is an identical as another state, let's say. But in one state, maybe there is a shark. There's a shark. Now that shark is potentially, let's say, hiding behind the rock. So the fact that the shark entered the rock is in your current state as T. In the next plus one, that is not visible. That information is not visible. Okay, you just see the rock because the shark really hid behind the rock. Okay, now condition history is going to allow you to form a better representation for ST plus one. Do you see what I mean? Yeah. But by the way, all this is going to be now. Like I'm explaining, now that we're about to train, let's say, latent stochastic dynamics, again, there's going to be a prior and the posterior. And let me tell you how they're going to look like. The posterior, which is the cheater, is allowed to look at everything in the video. It can even look at the future, to be honest, just to form a very nice representation for the present time step. And the non-cheater, which is this guy, is only going to look at the past, whatever it wants from the past. It will not have access to the present time step, so it will not know what actually happened, and it will try to predict it. Do you see? So now this is precisely what we're going to see. We're going to see these two networks. The cheating network, the inference network, will have access to the actual image. We'll know exactly what happened. Imagine you have stochastic environments. The monster may show up or may not show up. So the inference network will actually know whether it showed up or not. It has access to the next state. The prior will not have access to the next state, of course, right? And we'll try to put exactly those two losses together. And this is going to be happening at every time step. For every time step, we'll have exactly this. Is that clear? So let's see how this is going to look like. Okay. So our goal is to form a probability of the data probability of observation, given actions, regional observation, omega 0, okay? And we'll break that probability distribution as predict observations for states, stated dynamics, next state given previous state in action, and the probability of the initial state as 0 given the observation. And imagine that test 0 is, let's say, fixed. Then we have the following approximation. The log of the probability, this is the conditional likelihood of the data, the probability of observations conditioning on actions, okay, is this larger because we push the logarithm inside the expectation, okay, of reconstruction and minus the KL. So let's see how exactly this works. If we understand that, then we're in a good shape, I think. We have a conditional likelihood of observation given actions and the original observation omega 0 that for now we can assume constant, so we put away. Okay? And that probability is the central probability of observation at every time step given the corresponding state. All right? And now we're going to multiply and divide with the Q network. This is the cheating network. Do you see how we fit it into our conditional data likelihood? We multiplied and divided. Is that clear so far? Okay, so far there is absolutely no approximation because the logarithm is outside of the expectation. Okay. All right. Now, maybe before we move on, we need to look at whatever this the cheating network is conditioning on. Look what it's conditioning on. It's trying to predict what happened at time step t, and it's conditioned on the observation at time step t. Actually, it's conditioned on all possible observations. It wants to have maximal information. I'm trying to predict the observation at time step t, but you know it may be a baby behind the car, a dog under another car. So I'll condition on all the history, so I will know everything about, including what actually happened. So now I know whether the baby jumped out of the car or not, because I'm a cheating network. I can look at what actually happened at time step t. Okay, so this is Q. Now look at our prior here. That doesn't have access to actual t. So this is our prior with the dynamics essentially. Okay. It only conditions on the previous time step t minus 1 and a t minus 1. All right. So now, essentially, if we push the logarithm beside the expectation, it's a big multiplication. So the logarithm of the multiplier is the sum of the logs. And here we have a bunch of logs that essentially predict observations as well as reverse from the latent state. Okay. And we have the KL term between the posterior, which is the probability of the state condition of all observations and actions, including time step t, and the prior, which is the prediction of the state of time step t conditioned only on the previous state st minus 1 and a t minus 1. So now we'll see in more visual way how exactly this works out, and we'll also look at the network details. Okay, but roughly, does this make sense? Okay. All right. So essentially, our prior essentially has a transition model that just predicts the next state, and a decoder that predicts observations from that state. So let's see how we're going to do it. Dreamer did the following, let's say, innovation. Let me explain. Previous models, either they were deterministic, and how can you build a deterministic model? Essentially, you can do an RNN or an LSTM that conditions all previous observations you've seen and just predicts the next state. Okay. Or they were all stochastic, so you would sample and then you will sample the state in the future. But what they did is the latent state is some part is deterministic and some part is stochastic. So this deterministic part is identical to what other people have done. It's just an LSTM that doesn't forget and so on and doesn't go through sampling. And that HT actually is used to sample the Z. Is used to sample the Z. What actually happened? So essentially you try to predict the future in a deterministic fashion. Okay, and this is what HT gives you. Now from that HT you sample the ZT, the latent part, and then you condition on it to predict the rest of the quantities. Okay, as well as to predict the H that comes next. Do you see? So you use the H, you predict the stochastic part, so you need to commit on something, and then based on what you sample, which is what you committed from all the possible, let's say, futures, you use that to concatenate with the current deterministic part of the state to predict the next stage. What's going to happen now in the future? Condition that I think that the master action showed up. Okay? Yes.
So semantically, it's just like separating what you know will deterministically happen in the next state from what may be random.
Yes, exactly. So they say some part of dynamics is deterministic and I don't want to lose it. I don't want it to go through sampling, and some part is stochastic and I want to separate those. Yes. So let's go. Okay. So now we need to push through it to figure out exactly what's going on now. Okay. So here is how it works, guys. So we have H, and this H actually is just 30 numbers. All right. So imagine that I have built my H till time step t. And what I'm going to do with that H, well, let's see where the decoder is. Well, here, here's the decoder from a state. So my state is 200 numbers. All right, and from the state I can have a decoder method that predicts observations and rewards. All right. This is the deterministic path that predicts on what H, the next H. Okay. And let's see, different things are being used at training time and at test time. So these reconstructions over observations and rewards, this is exactly the reconstruction laws that I used at training time, is attached right there. And now we're going to discuss about the sampling of those views and sequence for the latent S. So we have a KL. We need to minimize the KL between the cheating posterior and the prior. So which one is the cheating posterior? And which one is the prior? Yes. So here is the observation OT plus 1. It fits into the encoder and maps to 1024 numbers, okay? And it's given here to the cheating network along with the deterministic signal to sample, the latencies for the state. Okay, so here is the distribution, then you sample and you commit a particular S. Okay? Is that clear? So this one cheats because it has access, it predicts the state at a particular time step, here t plus 1, having access to the observation at t plus 1. This one is the prior. It's trying to predict the signal for the next time step without having access to the observation at the next time step. It has only access to the H, okay, to the deterministic part of the state. Yes. Yes. So what is this previous state? Is the latent thing that previously you sampled, which you feed it as input to predict the next time step. So at test time, you only sample from your prior. You never use observations. At test time, guys, you only have the original, the observation of the first time step, and then you stay on the latent specs. Is that clear? You just feed one observation, the first image, and then you forget about observations. You just stay on the latent specs. Now, at training time, you will feed that an informed S for the next time step to help stabilize the training process. Okay, so the states that you're going to be feeding for the future will actually be the ones that you sample from the cheating network. Is that clear? But the KL is going to try to bring those cheating S's to the one sample from the prior. So at this time, you can throw away that cheating and just use your prior dynamics prior. All right. So what did we say? We said I use H, okay, to sample the latent part of the state, the stochastic part of the state, which is S, and then I use the stochastic part of the state of the previous time step to predict the next H. Do you see how the deterministic prediction happens, guys? It combines the current deterministic thing and the stochastic that you sample to predict the next one. Okay. All right. But this is just the deterministic part for the t plus 1. To get the stochastic part from the t plus 1, you take the H as input and predict the S. Okay? And at training time, you minimize the reconstruction error of observations or rewards and the KL between the prior and the posterior. This is precisely what happens in the code of that paper. Okay, now why we use both guys for the next time step at training time? Because you will be predicting multiple time steps in the future, right? So clearly, if your predictions are crap for the first time step, your predictions for the future also will be a little bit crappy. So we will use those S's that are sampled from the cheating network simply because they're going to be more informed. Okay, does this make sense? Essentially, we have a conditional VA for every time step of our network, okay, where we try to sample the stochastic part, which is the S, once from the H here, from where I think currently, I've already sampled the deterministic part of the future, and this is the HT. And given that I sampled the deterministic part of the future, now I'm going to sample the stochastic part, which is the S T plus 1. Does this make sense? And whatever I sample, I also fit the simple to predict my next H, as you see here. Here is the ST that I have sampled before and use it to predict the next deterministic part of my state. Is it a bit clear, guys, or no? How do you feel? Do you see why we call this the prior? Because it doesn't have any information about the next time step and tries to predict what's going to happen. What's going to be the latent part, the stochastic part of the state of t+1. This is the stochastic part. Okay? All right? So we call this the prior sampling. And why we call it posterior sampling? Well, because it has access to that observation t+1. It combines them with all information. And you may say, why does it fit this? We can fit whatever it wants. The approximate posterior can fit whatever it wants. Okay? Just to make an informed sampling of that stochastic part S. And the deterministic transitions is very simple. Here is what you have. You have your action, and you predict the next stage. Now, along your deterministic only pathway, you take your previously sampled latent part, and you also feed it as input there. All right. So I think the right way to familiarize yourself with this is to have homework. Otherwise, it's a little bit difficult, I must say. But I mean, to my best of my capability, this is the diagram that explains what happens in the code. Okay. Now the rest of the network is actually kind of simple. Training the critic is particularly simple. You go in the latent space. We sample, we set tons of trajectories. Everything is from imagination. This expectation is over sample trajectories. Okay. Yeah. And then either you evaluate your V based on some of instantaneous rewards, or you combine instantaneous rewards and your V estimates, or you have a weighted sum of multi-step returns for different horizons, which is not, it's something that we haven't seen before, but it shouldn't be, let's say, too confusing. I mean, it's just a combination of instantaneous rewards and estimates of the V, or the value function. So if we want to put everything together, this is how things look like. Okay. This is the dynamics learning, where we use this to learn the transition function, essentially. Okay, using environment interactions. Here is how we compute the critic. Here's the critic, sorry. And here's how we compute the actor by propagating through the values of the critic, the value targets. Then we are updating in this way our actor, and then we go and compute more environment interactions. And they say we explicitly add exploration noise to the action to be able to maintain sufficient exploration. All right. So this is what Dreamer does. Now, if you see what happens is Dreamer V2 versus Dreamer V1, we have, as you said, a huge jump, as we see a huge jump with a lot of model-free methods in between. So Dreamer V1 was a good first attempt to try to learn completely in imagination space and with stochastic dynamics. So let's see how Dreamer V2 changed Dreamer V1. This is insane. You know, an order of magnitude more use of imagination trajectories over actual trajectories. Okay, this is insane amount of trajectories. And just to be clear, how these trajectories are computed? You give me an actual set of observations. I feed them into my encoder. Okay, I jump into the latent space. The latent space has one Z part and one deterministic part. Okay. I transition here or H. I use the deterministic part to sample the Z the way we said, which I concatenate to predict the next H, and so on and so forth. Do you see? So you sample and you say, oh, I think the master is going to show up. Okay, great. Given that the master is going to show up, what's going to happen next? Oh, I think the stroker is going to fall down. Given that the stroker is going to fall down, then what's going to happen next? So you use the H to predict the stochastic part, and then you concatenate your prediction to predict the next deterministic and later stochastic part of the next time step. Do you see? This is very important because we need to commit overall alternative futures. right? Either the strawberry will go to the left or we're going to go to the right. Let's say, does this make sense? So this is the why we do this sampling and then concatenation. And essentially you form long trajectories of this form, and this is extremely simple because you never decode observations during latent imagination. Okay, you just stay in the latent space and you decode rewards, values, and actions. Is that clear? Yes. Well, they start, I think, from all zero, let's say, something like this. Yeah, all 30 values are zero, and then you start. That's also typical thing we do for LSTMs and GRUs and so on. Are there questions? Okay, so this part of this is clear. What's happening if I have the model, right? This is great. Now here is the new thing. We're going to throw away all these Gaussians, whatever we learned today, and variation of and so on. And instead of Gaussian latents, okay, different, you remember this mean vector, right? And covariance matrix, we're going to have a discrete latent state. So what does this mean? This means that my latent state will be comprised of 32 variables, and each one of them will be sampled from the 32 categorical distribution. Okay, so we're going to, essentially our network is going to, our H network to sample this is going to be forming 32 softmaxes. Okay, these are the distributions, the discrete angle of the Gaussian distribution. Then there's going to be a sampling. So what's going to be during sampling? Once I sample, instead of having 32 distributions, categorical distributions, I have 32 one-hot vectors. And those one-hot vectors now are going to continue and move around in the network. All right? Does this make sense? Yeah. So exactly this is what you see here as one-hot vector. So this is on and the others are off, and this is on and the others are off, and so on and so forth. And these are 32 long, and they are 32 in number, and this is complete coincidence. Okay? How many variables will keep and how long your categorical distribution is going to be? It's just that they're both power of 2 here. That's why it's like, okay, they're 32. Is that clear so far? We do know how to backpropagate. We'll discuss about this, right? I mean, we spent so much time trying to think about how to backpropagate through Gaussians, right? Are you so far okay with these latents? All right. So again, look how simple the diagram, how, removes all the unnecessary details and just tells you, you're going to have your H spitting out the stochastic part of that time step. Okay? It's trying to predict whether will the master go to the left or to the right. Now, you are actually going to see where the master went. And you're going to be predicting the corresponding stochastic part. And you're going to be minimizing the KL between the prior and the cheating posterior. The posterior is the one that takes into account the observation. Is that clear? Why? Because when you plan at test time, there's not going to be such pathway. The observation is never going to enter. You need to imagine everything. Is that like exactly like we saw 2 slides ago? In that high level, do we understand? Like, do we really feel that the same KL that we had before is the same here? Okay, we have a prior that has this in the future and is trying to predict it, and then we have a posterior that actually has seen the future, knows what it is, and then we try to put these two together, and then at this time we throw away the posterior. We just sample from the prior at every time step. All right, and so, by the way, here that we're also decoding observations. This is the reconstruction error, the observation and reward reconstruction error. Now, because at this time there's no reconstruction error, I'm also not going to be decoding observations. So clearly the decoding of the observations happens at the training time. Who thinks that it is useful to decode observations at test time as well? Okay. Okay, so what are going to be the, yes, please.
You could use it as like a measure of how far you've diverged in your latent space.
I see. I see, but first you need to plan where you haven't seen the future and select something, right? And then we're going to play it and you're actually going to see what happened, right? And you're saying, oh, I want to compare what I thought it was versus what it is, right? And see that, oh, out of those imagination trajectories, actually this was the correct one. Is this what you mean?
Yeah, it doesn't make as much sense.
I mean, it makes a bit of sense, although it's a little bit late at that point, all right? Because you thought that something else will happen. Oh, well, something, you know what I mean? So in any case, you may realize that things are going wrong because your reward is getting low, but yes, that's also exactly true, right? Yeah. Or you can put your value function and compare your value function, what you thought your value is going to be versus what it actually is, right? All right. But again, we have two sets of losses. So in high level, everything makes sense. Some reconstruction error, which reconstructs the rewards and observations from our latent states. And then some KL minimization between the prior that hasn't seen the future and the posterior that has seen the future frame. So it's at high level is the same. Why categorical latents are better than Gaussian latents? This is a very good point that is contained on the blog of the corresponding paper. By the way, there's also a YouTube video from guy Yannick, I don't remember his last name, which is very good. 1 hour long in YouTube. I think he makes only one mistake at some point, but other than that, is a very, very good to see and so on. And he goes through details, etc. So I think you're going to find it interesting. So here is what they say. They say if your model predicts a Gaussian, but the ideal prediction has multiple modes, then your unimodal prediction will never be close to the actual what the environment is. Okay. While with combination of categorical latents, your model prediction can be multimodal. Okay. And in fact, they mentioned in the paper, and I thought it's very interesting that everybody thought that training with latents, with discrete latents, is harder. And turns out it's easier than Gaussians because of this. Also, there's no this approximation problem. Okay, that you're actually being more multimodal in your predictions with latent variables. So let's see the details of how this happens. How do we train with discrete latents? Very good question. So this is what we need to do. Logics are essentially, you know, this that if you have 32 latents, categorical latents, you need to have 32 distributions. Okay, and each one is a set of logics, and which you normalize and then you sample. And the truth is that this guy is not differential. Once you draw a sample and you map your distribution to one hot, you cannot backpropagate through there. Do you guys agree with this? Okay, so we cannot backpropagate through this, but this is what we're going to be using in the forward pass. So in the forward pass, we're going to have this part of our stage, have this distribution, sample from them, and propagate our 32 one-hot vectors forward. So this is the forward pass. Now, here's what we're going to do on the backward pass. This is what we're going to write in our code. So in the forward pass, what happens is this guy survives, okay? This and these are identical because the stop grad only affects the backward pass. Okay, so the only thing that survives is the forward sampling, which is indeed the one-hot sampling from the categories of distributions. Do you guys agree? Now in the backward pass, when we differentiate, what happens is there is no gradient here, so this guy is not going to be used. These gradients are going to be stopped, so this guy is not going to be used. So the only guy that's going to be used is this, which is the softness of the logic. These are the normalized 32 normalized distributions. Okay, so the backward pass will see as if you didn't push through one hot 32 one-hot vectors. It's so as if you push forward 32 softmax distributions. Do you see? So 32 categorical distributions, and you backpropagate based on that. And this is called straight through differentiation. This is very, very common. When you have discrete variables, in the forward pass, you sample from them, and you are exact. And in the backward pass, you pretend like you didn't sample and you just left everything soft. Is that clear? That's how the gradients are going to be computed. And the difference with the previous paper is that when you learn the policy, not only you differentiate end-to-end through your dynamics model, but also you take our standard non-differentiable policy gradients. This is an estimate to the advantage. SG, of course, you stop the gradient. These are just sub-targets. This is the value of the present state, right? And this is the view of a particular trajectory, which is the view of the action, and this is precisely the advantage. And they say that policy gradients are better for Atari, and by propagating end-to-end fluid dynamics is better for continuous control. Why this is the case? continuous control is these robot benchmarks. Let's say place this, pick up that, and so on. The answer is because in robot benchmarks, the dynamics are deterministic. Okay, so it's much more, let's say, effective to backpropagate your dynamics model. Like errors don't compound that much, while in attack there is insane amount of stochasticity. Okay. All right. Still though, all this learning happens in latent space. Do you see all this learning happens in latent space, and they also encourage high entropy of the policy. So you've seen this before in A3C. And the last thing is this. So when you try to compute the KL between the approximate posterior and the prior, the cheating and the prior, they break this in two terms. In the one term, they stop the gradient in the first, in the other, they stop the gradient in the second, and the alpha is 0.8. Why? Because they say in the beginning, the prior that has not seen the actual observation is all over the place. It's very uninformative. So they say if we just try to put both distributions close to one another, the informed approximate posterior that has seen the observation actually goes towards the bad prior. So say I'm going to freeze for now, the approximate posterior and train first the prior, and later I'm going to change that alpha throughout training to train, let's say, the posterior. Okay. So they study this scale balancing, so you can check it in the paper. Now the result out of all these details is that they have a much better, let's say, performance. Okay. The rainbow is just a very fancy, let's say, lots of tricks of model-free learning, deep networks. That's all the details for today. Check the papers, and we can answer some questions next time, which is on Wednesday. On Wednesday, we will going to see some much easier lecture again, so please look up. Graph networks for model learning, very simple and very nice. Then we'll conclude the section of model-based, and then we'll start talking about intelligent exploration, which is super fun and very simple.